Hey, what's up, guys? I've got Noah here with me today,
Hey guys.
and today we're going to explain what MC Escher's tessellations mean in geometry. So we've got three basic equations right here, all having to do with the variables n, k, and pi, and I'm going to let Noah explain what those mean.
So, in tessellations, there are only three possibilities to put shapes together in order to form patterns without spaces in between. So we have three variables here, n, k, and pi, and each of those goes into each of these equations in order to find interior angles. But that's not what matters right now. N stands for the sides that each shape has. In this case, we can see that this 3 comma 6 represents three sides, for example, a triangle, and 6 lines connect to each vertex that six lines meet up at. So you can see, for example, that a hexagon forms around a central point. If you look at one point, you can drag 6 lines off in the direction. Same for the squares, same for the hexagons. I'll turn it over to Julian now.
Alright, so the reason pi is involved is because pi is used to solve things with circles through a degree of 360. And like here, there are 6 triangles, and they're all equilateral because that's the only way they can all fit together. So they all revolve around this one point, and since it's equilateral, it's also equiangular. So every angle is equal to 60 because 60 times 3 is 180. And that's the total degrees of a triangle. But if you multiply 180 by 2, you get 360. But,
Right.
So you need 2 triangles in total to create a 360 degree. However, we're only using one of the angles, so you need 6 of them. So that's 6, 12, 18, 24, 30, and 36 for a total of 360 degrees around rotating around one point. Same thing with the squares, except it's 90, so 9, 18, 27, 36. That's 360, and same thing with the hexagon. So that's why pi is involved. As for these equations only prove that these are the only 3 tessellations that work. There are other tessellations, as you can see, like 5, 4, 4, 5, 6, 4, and 5, 4, but those are all hyperbolic, so you don't need to worry about those. All we need to worry about is these 3 tessellations. I am going to show you an example of these tessellations. So, as for starters, I'm going to use the first equation, being k times n, it's k times pi times 1 minus 2 over n. And so that's the first equation. All we need to do is input all we need to do is input k and n, just as Noah said. So as n and k, as already listed off for us down here, 3 and 6. So 3 is n, and k, and 6 is k. So what we have here is k times 6 times pi, times 1 minus 2 divided by 3. So if we do all the math right there, then we can get 6 times 3.14, that'll give us 18.84. 18.84 times 1 minus 2 divided by 3. 2 divided by 3. Yeah, it's 0.6 and so forth. 0.66 bar. Okay. So, once we have that, we can have 1 minus 2 divided by 3, and we get 0.3 bar, so then we get 18.84 times 0.3 bar. And so if we take that and multiply it by 18.84, we get 6.28. Now what does that mean? Well, this equation equals 2 pi. So if we take our answer, which was 6.28, 6.28, and we compare it to our 2 times pi, 3.14, that equals 6.28. So that proves that the triangle postulate works. Of course, this will also work for the 4,4 and 6,3. Noah, do you want to show the other two equations?
Alright, for our second equation here, we have 2 over k equals 1 minus 2 over n. And we can plug in the variables that we had before, but instead of 3, 6, we'll use 4, 4 for all intents and purposes. So 4 being n and 2 being k, we can deduct 2 over 4 equals 1 minus 2 over 4. So 2 divided by 4, that would just be 0.5, that's half, equals 1 minus 2 over 4, which is also half, 0.5. And now if we simplify that,
We get a half equals a half.
Yes.
Which checks out.
Yep. And for our third equation, we have 1 over k plus 1 over n equals 1 over 2. And we'll use the third tessellation, 6, 3. So we'll have 1 over 3 plus 1 over 6 equals 1 over 2. Now we'll have just 0.3 like we did before. 1 divided by 6, 1.6 R7.
1 divided by 2. And if we add those together, what do we get?
So if we have 0.33 plus 0.166, it'll get to around 0.5, and if you get a little deviation, that's just because it's a slight rounding error, equals 1/2, which is to be checking out to our equation.
Alright, that's cool. So we know that all 3 equations work.
And that's how you can prove that a tessellation works in the case of Euclidean geometry. Remember, hyperbolic is quite different from the non-spherical planes in Euclidean. So keep that in mind as we move on.
Yeah. Alright, so here we have an image of yellowfish and green frogs. Over where all the frogs' feet touch and some of the fish's mouths and fins touch, we have an intersection of 6, just like our triangle postulate back here. And if we connect all of them, you'll notice something interesting. Because when I connect all the nearest ones to each other, we get a total of 6 lines. And it's interesting because from a single point we get 6 lines coming off of it. But if I connect all of these yet again, we get 6 triangles, just like our postulate. And if I keep doing this, then I get more triangles, like that. Of course, I could keep doing this for a long time, and eventually come up with a big grid. So I'm just gonna do that, and I'll get back to you. So here, I've done all the possible hexagons I can do because I can't see any further intersections, and I've also labeled all the triangles dominated by the green. The green frogs as 1, and the ones dominated by the yellowfish as 2. So we can see that even though these tessellations are hyperbolic due to the curved lines, it still resembles Euclidean. Noah, do you have anything to add to that?
No, not at the moment, no.
Alright, so I'm going to go ahead and switch over to this one, which I have already filled out. But however, there's something wrong, Noah. Do you think you know what it is?
It appears that not all triangles seem to be equilateral.
Yeah. Do you know why this is?
No, Julian.
Oh, okay. Whatever. Anyways, it's because
It's
this image is extremely more hyperbolic than the last one.
well, because you can imagine maybe that.
Because, see, there are absolutely no straight lines in the outlines of these yellowfish and these grayfish. It still has the triangles of yellowfish and the triangles of grayfish, 1 and 2. Um, so we can still tell that it is a nice tessellation, however, it lives in the hyperbolic world, much like these ones, where they have curved lines so they can get these extreme results of like 6, 4. That's the difference between Euclidean and hyperbolic forms inside of tessellations. Hyperbolic can range from any different shapes or sizes. It doesn't, and they don't have to be equilateral triangle in the sense of triangles. Alright, then that's it. Alright, thanks for watching. Bye.
See, kids.